This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
So welcome to the Math Map Book Club. Today's Wednesday, February 11th. I'm Lee Borton, and this is where every week Kirsty Gilpin and I, along with our team of enthusiastic parents, talk about the Math Map and what's going on in our curriculum that's being used by Classical Conversations families across the globe. And I just wanted to share some fun that I had this week. I was at dinner with 6 different challenge leaders, and they were loving the Math Map. And I asked them why, because, we hear all kinds of things. And the one gal said, well, as a Challenge A director, I invited all my parents to go through 2 lessons with me. The kids came over and went and played, and the parents did the lesson instead of the children. And so that was very effective in that region. And so I just wanted to encourage folks to not give up, but to work like we're supposed to be doing as the body of Christ together. This is for our sake more than our children's sake, because we're the lovers of Christ and know how to work as a body. So I just appreciate everyone who's putting the time into this. And thank you to this team that just shows up week after week.
Well, we appreciate you, Lee. All right, and so here we are. We are looking at lesson 23 this week, matrices. And for those of you who have some advanced math knowledge, matrices are sort of the backbone of linear algebra. And so if you are somebody who is looking ahead or wondering about sort of the advanced math that's in the math map, matrices are a really helpful tool that we can use to solve systems of equations and as well as to organize information. But they also have a really sort of almost an outsized application when it comes to to computer systems, because computers don't necessarily think in 7x plus 3y minus 7, but they can think in the numbers, right? The 7 and minus 3 and whatever other number I said. So they have this great application that are used. And so linear algebra courses are a big deal. And the goal of this lesson is to help us see how we can use mathematical tools to organize these dimensions that just get unwieldy, right? We've talked a lot about how just in 3 dimensions, as soon as we add that third variable, there's a lot of moving parts to keep track of. So now if we add a 4th dimension or a 5th or however many dimensions, there's a lot of moving parts. And matrices are a really great tool for helping us organize that. And so along with the rest of the math map, remember what we're focusing on is that language of mathematics. If you're somebody who is less familiar with mathematics and perhaps less familiar with matrices, remember that the goal is to get the language. If your students are going to go on and do any further studies with mathematics and they end up with some linear algebra courses, they're going to be well prepared for that because they're going to have the grammar, right? That basic vocabulary that they would need. So if you come into this with some background and are looking at where this fits into that bigger picture of mathematics, that's where it fits in. If you're coming in going, I've never heard of matrices or it's singular matrix, then beyond the movie perhaps, then rest assured our goal here is just to look at the language. And every week, we really want to emphasize the grammarian nature of what we're doing here, that importance of having that grammar before we try to become dialectic. Right? We can't ask good questions if we don't have some base knowledge about which to look for patterns or ask questions. So flashcards are just the most efficient way that we can load that grammar in. And when we think about flashcards with mathematics, probably a lot of us are familiar with the addition and the multiplication flashcards, using flashcards to practice our calculation facts. I'm really excited that Lee and Classical Conversations has decided to invest in flashcards that go beyond those calculation facts. The notations, I think, are probably one of our most popular because it does get at the heart of the symbolic language that mathematics is. But notice that now we're also looking at exponents, roots, and logarithms. And in just a couple of months, we're going to start seeing the trigonometry flashcards along with the algebra flashcards. So those are going to be bringing in a lot of grammar that are not computation based. And copywork and some tactile expression are some great ways to engage with those cards. You certainly can do that with the math facts, but you could, especially with those notations and some of these other flashcard sets that we're coming out with, having your students copy or having them model, right, with Legos or Cheerios, right, using some kind of tactile expression, the traditional stick in the sand, right, that Lee's always talking about. When my children were young, we lived in Florida, so we oftentimes ended up on the beach. And we were always literally doing our homeschooling with a stick in the sand, right? Not not to be funny, but because we could. We had a whole beach usually to ourselves because all the kids were in school. And so we could do all kinds of things on this huge blank canvas. And we can do that with the flashcards are a great way to get some content in which to do that, right? So giving each of your students a flashcard and say, okay, right, use Legos to build this, or use your cars, right, in the sandbox to draw these shapes or these symbols is a great way to take those flashcards that may be unfamiliar and help that unfamiliarity turn to familiarity, right? That's a great way to do that through copywork and expression. Anybody have anything they'd like to share about flashcards this week?
Well, I was just going to add to what you were saying about that. I think I've shared this before, but last year in when we did our blue books for Challenge A, I brought in cookie dough, sugar cookie dough, and they would choose notations to create with their cookie dough. And then some chose to eat it afterwards, some chose to throw it in the trash. But whatever, they used that as that tactile, expression. So I thought that was a fun way. Somebody shared that they did it, so I copied it, and it was it was really fun.
That is fun. Yeah, and Play-Doh, right? If you don't want your kids eating it, you could use some Play-Doh, any of those types of things. Getting them to engage with it in a different way may invite students in who aren't as excited about flashcards. This is a way to invite them in a different way. And that brings us to our cover for this week. So our lesson is matrices. Matrices is the plural of matrix. Right? So if we think about our Latin, where we have those stems, right, with the X, and we're going to replace that X with the CES, we're making it matrices. And a matrix is an arrangement. That's really all we're talking about is a lesson on arrangement. It's a very specific arrangement that follows some patterns and follows some rules that we're going to look at this week. As we look at our cover, when we think about our 15 skills this week, we're looking at our skills that come from our invention skills. So those are our common topics of invention. And our first one is definition. So what words are needed to describe the art? Notice that we're connecting that idea of definition with words, which is similar to the idea of naming, because we're talking about making sure that we name things with the correct word. Definition maybe takes that a step farther because we want to make sure that we're using the words correctly. Does the word say what we mean it to say? And so when we look at our art, what words can we use, or what words are needed to accurately describe the art?
Hey, Kirsty, is there another term for matrices? Have you ever heard them called anything else?
I don't think so.
Yeah, I was trying to think. I can't think of any synonyms.
As we look at our covers, our next common topic would be comparison. And again, we've talked about comparing what is the same and what is different, but we can take that question a little bit further by asking our students, what do you learn from what is the same and what is different? Why do you think those things are the same? Why do you think those things are different? What does it mean when we see repetition? And you could do that from week to week. Right? If you have students that, if you only have one level of the math map that you're using because you either just have one student or your students have to be in the same domain, then you can ask them just to look from week to week, compare last week's to this week's lesson, right? What's the same and what's different? Or if you have multiple students, this is a great way to encourage them to engage with their siblings' covers, right? So what's the same and what's different on your siblings' covers to help them address those things that are the same and that are different. For circumstance, thinking about location, we can ask, what does the where of the art tell us? So you may need to do a little bit more research. You can look in the companion or do your own research if it's not in that description on the side. But looking at a piece of art, and especially as a photograph, where was this photograph taken? This isn't the totality of the place. So where is this located? And what might that tell us about the art? You can always talk about order when we talk about relationship. And to switch it up a little bit, instead of talking about necessarily the elements that are on the cover, ask your students what order of discussion do they prefer? Do they like to look at the art together first? Do they like to look at the quotation first? Do they like to look at the reflection first? Right? Which one resonates with them? And do they like to do that first or do they like to do that last? Right? So there's generally two schools of thought amongst us, right? If there's something that we really like, we sometimes want to do that first and procrastinate the things that we don't like. And then the other school of thought is that you save the best for last. Let's get through the things that we struggle with and save the best for last. So asking your students to think about the order that they like to work in helps them to think through, right? How do they order themselves? Because of course, that's our ultimate goal is that our students can order themselves. And then we've discussed this quite a bit in the office when we think about our quotations and our reflections a little bit less, but especially the quotations, that sometimes the author of the quotation um, isn't necessarily somebody that we really like or that we always agree with, right? We've tried not to include any very controversial authors, but when we look at those authors, right, we may not go, oh, that's somebody I really, really like them. So I'm going to believe what they say. So ask your students if you see somebody and you're not sure about the person, or you don't know who it is, or it's somebody that you're not sure you like, or you don't necessarily agree with them in everything that they say, does it affect the truth of what you're reading? Can somebody who's wrong, even right, somebody who's kind of wrong, still say things that are right? Can we learn things? Can we see truth, right? That truth is transcendent, right? That's why they say it's a transcendental, because it transcends the idea of the author, right? That all truth comes from God. And so he can reveal that to us in a lot of different ways. And so asking your students and helping them to work through that, right? Can we be convicted by something or can we recognize truth, even if we don't necessarily agree with the author?
That's a bigger lesson than the math map for sure. I mean, how many people are being canceled because of different things? And we're not perfect, so we're not going to agree with everything everybody says. So that's a good lesson.
Yep. And then every week we encourage you to start your week by looking at the math map itself. And as we look at that, notice that we had talked about in the past um, that this checklist is in every book for the foundations domains. So this week I wanted to really emphasize that the same order, the same checklist is in the guides for the challenge domains. Okay. So everybody has the same order of working through the booklets. It's just where it's located. In the challenge guides, we're moving towards ownership, right? So in challenge A, we start off our themes with ownership. So we really want to move from mom directing everything that we do to the students using that guide to say, okay, this is what I need to do today, and working through that. So same checklist, same order that we're encouraging you to work through the booklets, but those challenge students are going to find that in their guide where they're being invited to take ownership over that work. Note as we look at our math map this week, we are in 4D. So we had 4 quick weeks in 3D, and now we're looking at 4D. None of us really knows what 4D would look like. But we had a really great conversation yesterday with a director because her student was talking about things that were open in or closed in one dimension being open in the next. And she said, so if we're closed in 3D, what does it mean to be open? And the Lord in his graciousness brought to mind that Bible verse where the Bible says that God doesn't look at the outward man, but he looks at the inward man. So we being stuck here in 3D, I can only look at the outside. Now we know that your outside may be reflective of what's on the inside because it says that out of the overflow of the heart, the mouth speaks. So we know that your outside is going to reflect what is on the inside, but it's not transparent. And a lot of us can act good for at least a little while. So we can look at each other and not really know what's going on the inside. But if God is outside of 3 dimensions, right? And the Bible suggests that he is because it says he can see inside, right? That means that all of us is open. So why are we looking at the 4th dimension, right? Well, because there's biblical evidence that God is not restricted to 3 dimensions, right? There's biblical evidence that God inhabits something beyond our 3D-ness that makes us open to him. And so if that's the case, maybe we should study that and understand a little bit or catch a glimpse a little bit of what that 4-dimensional space might look like. And so we're going to start by looking at matrices because they help us to organize lots of material that we find when we're having our four variables or 5 variables or however many variables we have considering our number of dimensions, that when we have all of those different pieces, matrices gives us a way to keep track of it and not lose information. So each week we like to take a look at our lesson pages and talk about the strategies. And so this week our strategy that we're talking about is using our solutions as copywork or to work backwards. Again, I just said we're moving into some lessons that may feel very unfamiliar to some of our families. Copywork is an easy way to start making the unfamiliar familiar. Okay? If this is unfamiliar and we don't know the grammar and we really aren't able to do much of what is on the page, copywork, right? Being careful and looking at the copywork is going to help make that unfamiliar familiar. So it's a way to introduce the concepts right? By looking at that solutions page. We can practice the notation and the forms. So for our younger students, if we're not reading with them and helping them just by practicing doing copy work, they're still practicing the notation and the forms that are used in this lesson. If we're working with them or if they've become independent, then they're practicing their reading and they're practicing the attending at the same time that that unfamiliar is becoming familiar. So when we talk about copy work, we tend to think that we really mean to be attentive. But even if your student isn't necessarily attentive, even if they're just filling in the blanks and not paying attention to the rest of the material on the page, they're still going to be making that unfamiliar familiar. They're still going to be practicing notations. They're still going to be practicing forms. But we can press that a step ahead by really emphasizing that they are reading and attending to those blanks that they're filling in. Now, copy work is a little bit different to working backwards because working backwards suggests that I'm not just copying, but that I'm actively working to try to figure out how to do this, right? I'm actually trying to see, well, how was this done and how can I do this independently next time? So it's a little bit different from copy work. It's almost a little bit more of a dialectic skill than a grammarian skill of just copying. And it works because sometimes knowing our destination can help us to map the route. I oftentimes think about Abraham being told to just go to the land that God would show him, right? Just go. And I think, I know my question would be like, go where, right? I want to know where I'm going. What is it that I'm trying to get to? Even if I decide to take a scenic route, even if I try a different way to get there, I kind of like to know where I'm going. And so working backwards sometimes helps us to go, oh, that's what they meant, right? That's the type of answer I'm trying to get to, right? So seeing that destination helps us to map the route. Looking at the solution can give us hints as to which strategy to use. It can give us practice in attending to the steps because now I'm not just copying, but I'm looking at the totality of the solution that Lee has included. And so I'm looking at that solution and I'm going, oh, that's why they did this. That's why they did this. I want to pay attention to the steps. And if I'm working with my student, it's a great opportunity to say, well, why? Okay, this is the solution, and we're looking at their solution to this exercise. Why did they do that? Right? Why did they make that choice? Sometimes there's more than one way to solve any particular exercise. There may be more than one way to show how you've simplified a fraction, for example. And so this is a great opportunity if you're working together to ask your students, well, why would they have chosen that? Would you have done something different? And so discussing the why when you're looking at the solutions is a great way to use that. Anybody have anything they'd like to share about using our solutions to
Yes,
help
I
them
do.
learn?
So I want to remind families that to make your work easier as a parent, I would take the solutions out first and look at them because the amount of red will tell you what's really being expected from the child. And then the solutions are on just 4 pages, so it's not like a whole lot to look at. So it's a brief way to preview what's going to be expected of your student. And then that way you have the solutions, whether to give them, because you might go, you know what, this is a tough lesson. I actually want you to forget the booklet. I want you to take these 4 pages of solution and I want you to write out all anywhere there's red steps. I want you to write those problems out. Right? Practice the form, practice the reading before you try to solve it.
That's a great reminder. Even taking those where there's steps shown in the solution, Lee, and writing it on a separate piece of paper and separating those steps out, right? That's another way that you can use that. It's still copy work,
Mhm.
but now we're expanding it and we're showing how the different steps are laid out.
So
So
for an example, we could have not called them solutions. We could have called the solutions page example problems.
That's a great reminder.
I'm glad you guys touched on that because that's literally what I had to do in Kirsty's elementary number theory class is like study the answer key because it was so hard just reading the chapter and looking at their examples, it wasn't enough. So I really did have to study and copy and just look at those problems over and over again to try to figure out how to do the rest of them.
I mean, it's no different than telling your child to make their bed when they've never seen it made right. You always want to look at the solutions when you're new to something. It's just common sense.
I appreciate that, Lee, that it is common sense, but that's not how it's been taught for decades, right? Because our math education for decades has been chopped up, right? And so you learn a little bit of grammar, you practice a little bit, and you take a test, and then you learn a little bit more instead of being able to see this big picture. And so I really appreciate what the math map gives us in allowing us that time to really look at the solution, to look at what the forms are before we're expected to do all of that work. And so having patience not only with ourselves, but with our students as we work to get to that is really important. So looking at page 1 of our lesson this week, you'll notice at the top we're taking a minute and looking at a section that's very similar to what we've seen in our other dimensional introduction lessons. So if you look at lessons 1, 3, 9, 19, and now 23, they're all going to introduce, right, the dimension that they're in. They're all going to have not lesson 1 because it is a little different, but the other lessons are going to give the students that opportunity to pause and acknowledge that we're moving into a new dimension. And so that's what we see here at the top, right, with our tesseract. Now, we don't know, right? We don't know what 4D looks like. We can only picture what its shadow might look like here in 3D. And so that's the idea behind a tesseract is that maybe this is the shadow of what the fourth dimension might look like here in 3D, right? And so that's what we're thinking about there. One of the things that I like to remind myself of, as well as others, whenever we're talking about going into 4D, is the idea that um, when we think about a line, we usually can kind of conceptualize an infinite line, right? We think of an infinite line, and if you have another infinite line that intersects it, you have an infinite plane. And we can conceptualize this infinite plane, right? And then we can say, well, if there was another infinite plane, and we go, well, yeah, I can see that, right? Because I can have this wall of my house and this wall of my house. If they went infinitely, they'd be two infinite planes, and they still fit within my 3D system. So I can picture that. But now, once I get to 3D, and I've talked about how I can have two infinite planes within 3D, we need to remember that our real space, the space we inhabit, is finite, right? There's a boundary to our universe. It isn't infinite, which to me always poses the question of, okay, well, what's beyond the boundary, right? Like, isn't that kind of a weird thought? But we know that there's a boundary to our universe. But mathematically, 3D space is infinite. So if I think about, right, in 2D, I can have two lines. In 3D, I can have two planes. So in 4D, I have to be able to have two spaces, two infinite spaces. And what we end up doing is we draw cubes and we draw things that look finite, and we go, oh, well, I can look at two tissue boxes, right? But those tissue boxes are finite, and so they can exist in the same 3D space. But if my 3D spaces are infinite, right? There's only room for one in this space. So I don't know what that other one looks like, right? What does that look like? But that's what we want to encourage. Maybe not our youngest students, right? But our older students, we want to say, okay, what's the pattern? Well, if the pattern was I have 2 points and they can exist on a line, and can have two infinite lines that exist in a plane. Really, we know there's an infinite number, right? Well, then there's two infinite planes that can exist in space, my 3D space. Then there have to be two or infinite, right? So there's a mind bender through infinite 3D spaces in 4D, right? And so playing those games with your students just to look at the different ways that we go along. Um, a couple of weeks ago, we saw the Play-Doh, right? Stretching that Play-Doh. So if the idea is that I could take that point and I stretched it, and then I take that line and I stretched it, and then I took that line, that plane, and I stretched it, how do I take my 3D space and stretch it? So, right, none of us knows, but those are some great ways to talk about it with your students just to help them see the power of mathematics is the patterns, that we can see these patterns and we can say, okay, well, these things are true about 0, 1, 2, and 3D. These things are going to be true about 4D. If I have no variables in 0D and one variable in 1D and two variables in 2D and three variables in 3D, how many variables would I have in 4D? Right. So I would just encourage you, if as you're looking at this and 4D feels overwhelming, to take a minute and just say, look at the patterns. What patterns do we already know? And they can be very simple patterns with our younger students, or they can be challenging patterns with our older students. The rest of the page, we're taking a closer look at matrices and how we set matrices up. Does anybody have any questions on anything here?
Yeah, I have a question for you. So, we've been saying that to each other for 9 years now that, then 1D, 2D, 3D, 4D, you should be able to bring the patterns into 4D. But just because you should be able to, are there like mathematical proofs where people have tried to say you can do it? So for instance, I may not be able to spatially view a tesseract, but can I with all integrity say, but whatever the axes are and however you draw them, they're probably all at 90 degrees to each other, just like they are in the other dimensions?
I don't know if we would be able to necessarily prove that, but by the way that we define it, I think that we
Mhm,
would all agree that that is
mhm.
true.
Okay, so if I go and I say, I'm going to do some sort of 6-dimensional studies, I could begin with saying, okay, there's probably going to be six of a bunch of things. What do I already know those things are? What would they possibly look like? Because the place where I feel like that has broken down in our conversations is the forms of the equations for vectors drawn as parameters are always the same no matter what the dimension is. But when you do like a 2D line versus a 3D even simultaneous equations, there's different forms that some work and some don't.
Yeah, I think without looking at specifics, I think there's a lot of things that yes, we know
Mhm,
that in 6D, we would have to have six coordinates for our vectors. And that we would have to use vectors to define our lines, and that we would have to have six variables in our six-dimensional space. And if we were to have an equation of a line, we would have to use vectors where we would have, the interesting thing is a line still just has 2 points, right? 2 points determine a line, whether it's in 2D or 6D. It's the same structure of a line. But now, in order to locate that line, I'm going to have to say, well, here it is in
mhm,
each of its six coordinates is this point, and a second point with each of its six coordinates is here. So
mhm.
have to be able to anchor things with 6 coordinates, even though I still only need 2 points to determine that line.
Yeah. So if you're doing something as simple as the sixth root of, say, 64 is 2, that somewhere there's 6 roots. Now that can be drawn on a circle, but that makes me also wonder, like, what does that really mean in 6-dimensional space? Like, I don't know.
Well, it means that if I had whatever my content, like whatever my figure would be in 60, right? My 60 figure, closed figure. So a polygon is our 2D closed figure. Our polyhedron, for example, is our 3D closed figure. So I guess it would be like a poly space something, right?
No. And then a polytesseract, and then a
And right, so we
polyquinteract.
whatever that looks like. If I said the sixth power of 2, well, I'm saying that I have 6 dimensions to that shape, whatever that
Mhm.
is, where each side is 2, right? So we can take the things that we've learned here in our 1D, 2D lessons. We see that those patterns hold for 3D, and now, oh, they're going to hold for 4, 5, and 6 as well.
Thank you.
Fun questions. Now, on day 2, as we look at our invention page, we're practicing our common topics. And as we talked about earlier, definition is our first common topic of invention that we usually list. Some people list comparison first. We're listing definition first. And 2 good questions that you can ask your students when they look at this page is, what can you define? And what words do you need to define? Right? So let's look at, if we look at this page, what are some words you can define on this page? And almost all of our students should be able to find some word that they can define. It might be the name of their domain that's up on the top right corner. It might be that they know what 3 is, or that 2 is a preposition, right? They doesn't have to be the math words, but going through and saying, what words do you know? What words can you define? And then what are some words that you need to define? We've talked elsewhere about how the dialectic skill of definition would be really working from the context to write those definitions, not just repeating a definition from a glossary, but being able to write a definition that demonstrates your understanding about the thing that you're defining. Versus the grammarian skill of definition is really going and looking it up, right? And adding to your memoria, what does this word mean? So we practice that on our I² page. And that should say that we're practicing the skill of, yes, definition there, right? That's what we're practicing, is a skill of definition, not the math concepts, but the skill of definition. Oops. And looking at page 2, notice again that we're looking at matrices. So we're going to just keep looking at matrices. How do we set them up? How do we operate with them? We're building up our skills towards being able to operate. But most of this is scaffolded in such a way that students don't necessarily need to know how to operate, right? They're simplifying, but they're simplifying within the form of a matrix. Any questions about this page? I do want to point out, I just think it's so interesting that I did not fully appreciate this before I worked with Lee on the math map, that those absolute value symbols that we use here for determinant are still a measure of magnitude. But where we've seen them before, they've really been a measure of a one-dimensional magnitude. Our determinant is related to a two-dimensional magnitude. I think that's kind of a neat thing, but we're still talking about magnitude. So we see these symbols and they're used in in different ways, but they all have that same fundamental meaning that it's telling you that you're looking for magnitudes. On day 3, we look at our I cubed, our memoria, and arrangement page. And this week, our core habit that we're exploring is expressing. And so when I think of expressing, I think artifact, right? That there's something I'm creating that's different to words. So when we talk about storytelling, we're using words. Expressing is an opportunity to do something other than our words. So it could be some kind of physical movement. It could be drawing pictures. It could be building models. So we have lots and lots of Lego at our house. So, right, building models with Lego. What do these things look like if I was to have Lego and build some models with Lego? And we can scaffold our expression by guiding and instructing that, right? So maybe you want to tell your students how to use the Lego or how to draw something, right? That you tell them, we're going to move this way. Whereas our older students, we can encourage them to come up with the expression. We can scaffold by always starting with the forms and the arrangement. So what are the big ideas on this page? How could we express those? Or how could we express the form of a matrix if we're not worrying about anything that we're doing with it? How could we express that? And then for our older students or our more familiar students, we could challenge them to express content or understanding, right? So that takes it a step farther and takes it from just memorization, right? Help working towards memorization and now building memoria because we're asking them to pull from that memoria as well as solidifying that memoria by expressing the content and the understanding that they have. Anybody want to share anything about expressing?
I was trying to think how, on that page we encourage memorizing. And so I just feel like a question is going to be, well, what in the world am I going to memorize on this page? But I feel like the top row, if you just broke it into chunks, you could, make your own flashcards, or I know some of them are already in there, but like, what does a matrix look like? And then, the different symbols. So I don't know. I always try to find something on the page that I feel like could be memorized so I can share it with the kids and say, choose something in this top row, and try to memorize it by next week or whatever. So I think that would be something for parents if they're looking for something to pull out to memorize. That top row looks like it would be, fairly easy.
That's great. Yeah, there's your essential grammar of matrices right there at the top. That's terrific. Looking at page 3, again, there's a lot of unfamiliar things this week, but if you look at the lessons, you're going to see that it's a lot of repetition of the same ideas, calculating determinants, setting things up in a matrix, copying, right, and looking at things. They're not asked to do much with these matrices yet, right? So we're just looking at working within the forms. So it looks like it's unfamiliar and it looks overwhelming, but if we pay attention, there's not a lot for our students to do, but the work that they're doing is within the forms of the matrix.
I wanted to add that, we had that kind of intense arithmetic section and only 7 lessons, and then we move on to the second semester. And here's an example where there is still so much review of adding, subtracting, multiplying, and dividing in every single one of these equations in the matrices, because that's what you do. You multiply and you add or subtract the numbers up over and over again. So for the littlest guys, you're seeing, they're still doing single digit with a couple of double digit because they're in 2nd grade, that age group. The middle level, still doing single and doubles, but there's some 4-digit numbers you need to read, but not really do much with. And then, of course, once you get to the monomials, their singles and doubles, but they're doing more of the steps. So there's still more calculating that needs to be done. And every time you're finding that XY, you're dividing what you've already added, subtracted, and multiplied. So all the fundamentals are reviewed in this lesson.
Lee, I really appreciate what you just said, that because one of the great things about matrices, why so many people like them, is that it gets rid of our variables, right? That we just use the numbers. So if you are somebody who does not enjoy algebra and all of the letters, right, which are just objects, but if you're like, I just want to do numbers, this is the unit for you, because that's what matrices do. They strip away all of those letters and let us just work with the numbers.
Yeah, I've told this story before, but I'm gonna tell it again. So instead of taking calculus, my math advisor in high school said, Lee, take a third year of algebra, take the advanced algebra course, which was super similar to Saxon. The Saxon was written back then. He said, because if you're going to go into engineering, this is the last time anybody's going to let you practice the basics before you start moving into those harder, higher levels. And I did. And so we got to the matrices. And I did, the homework, and I said to him the next day, I said, what? Why did you save these for us? It made math so easy. All the equations and variables disappeared. And he said, well, if we showed it to you when you were little kids, we never could have gotten you to do simultaneous equations. So a little bit of a trick there to the parents who are introducing this, because we are introducing it right from a young age, to tell the students that there really are two ways, and probably even more, ways to do almost everything in math. And so this is just kind of a restful unit because it's such a good review. And yet it's exactly what is used for 4 and 5 and 6 and 7 and 8 dimensional mathematics, because it's the only way to go about doing it.
And then on our fourth day, we have our careful calculations page. And this week, I just want to remind you that you can tailor your computation practice to your students. The careful calculations can be a great way to have a form to work with. Um, we always want to start by emphasizing their fluency with basic facts, right? So our addition and multiplication flashcards, you have to know those basic facts before you can start to do anything else, right? I need to really know what my facts for zeros through nines are before I can multiply any double digit number. We really want them to be fluent in basic operations. So before I start adding matrices, I need to be able to add two numbers, because adding two matrices is just defined right through that addition of numbers. So start by looking at our basic facts, our basic operations, those fundamental computations. What are the computations that they need to be able to do before they move on to compute with something else? Then you can challenge your student to compute with fractions, with imaginary numbers, with variables. So if you're looking at the math map or any math curriculum and you're trying to figure out, what do I need to do for my student, go back and start from the beginning and say, okay, can they calculate their basic facts? Do they have those memorized? Using the flashcards or a drill sheet, say, do they know their basic facts? Then say, okay, they do have those. Now let's go ahead and practice. Primarily what we're practicing is using place value when we are taking those facts and now expanding those to all of our operations, right? We need to understand our place value and how to line up our numbers. So now can I add, subtract, multiply, and divide? And then are there any other computations that I've seen that we need to come up a lot? Maybe I should add those to my memoria. And then as you're going, right, the next thing I would say is have your students demonstrate that they can work with fractions, then with imaginary numbers, then with variables. And if you're trying to target your practice, that's sort of a systematic way of working through the things that you can operate upon that you could do. Any questions? That's probably one of our most common questions that we get from people, right? Is how do I practice these basic things? And I think that the careful calculations are great in giving us forms, right? Because I can plop in different numbers depending on what I need my students to be practicing to help them see where those basic skills fit into some of these more advanced ideas. And then our four set, we take a look here. We're now, if you haven't noticed that vectors pop up over and over and over again, notice that they do. And Lee has almost always, not always, it's not 100% of the time, but almost always that fourth set of a unit is going to be an opportunity to practice with vectors. And so as we look here, we anticipate that if I'm in 4D, the fourth dimension, my vectors have to have 4 coordinates. And this might be where your older students, your more familiar students, start to recognize that the forms for our vectors are the same. That if I say vector 1 plus vector 2, I know that I just have to add the corresponding components. That form is the same whether I have a one-dimensional vector or a 100-dimensional vector, right? I'm always just going to match up the components and add them to get my resultant vector. If I'm scaling a vector, right, it doesn't matter if I have one component, one coordinate or 10 coordinates. I'm going to scale each coordinate. So the form of working with these vectors stays the same no matter how big they get. And that's one of the reasons why they're so useful for this multidimensional mathematics. Any questions on this page? All right. So as always, we want to be here to support you. We appreciate everybody who takes advantage of the companion, everybody who comes to the book club or watches the recordings, everyone who comes to our help desk that we make available for our tutors and directors. We really appreciate that. Next week, we'll be looking at lesson 24, then 25 and 26 are our 2 calculus lessons. And then in March, we'll be on the home stretch for this year's book club. We had one question that was sent in this week, and I thought this is a really great question. And a mom sent in and she said, well, my daughter swapped the length and width, right? She said that the length was 8/9 of a meter and the width was 5/7 of a meter, right? But it didn't match the answer key. And how do we know which is which? And I thought it was a really, we at the Math Map, and Lee has worked really, really hard to limit the number of exercises where the solutions say answers may vary. Right? Because she knows as parents, it's a lot easier to say, this is the answer. When we tell you to use the solutions to work backwards or as copy work, solutions may vary is not very helpful. And so Lee has really worked hard to not have a lot of ambiguous cases. But the reality is that there are times where there's an ambiguous case. And I thought talking about here we're coming into 4D, right? We say we have length, width, and height. And we generally said length was our 1D and width was our 2D and height was our 3D. But if you think about any object you have in your home, right? So let's talk about my cube, right? My tissue box, my rectangular prism. And let's say that this is my origin. And so when I first looked at this, I said, well, this is my length, this is my width, and this is my height. Because we tend to like the up and down to be height, right? So I have those. And so this is always my length, always my width, and always my height. Well, let's say I only wanted to look at these 2 dimensions. Which 2 dimensions am I looking at? I'm looking at width and height. If I only wanted to look at these 2 dimensions, I'm looking at length and width. if I wanted to look at this dimension, I have length and height. If I was just looking at one dimension, right? Let's look at, I can't make it just show one dimension, but right, this is just height. This is just width. This is just length. So I could, in my 1D, if I was looking at something that was in 1D, I could say my height, I could say it was my width, I could say it was my length. It doesn't really matter which one I call which thing. What I want to remember that it is that in 1D, I can have one measure, one long measure, right? In 2D, I can have two. In 3D, I can have three. So in this case, looking at this exercise here, if I swapped which measure went in which label, it's all the same, right? It doesn't matter if your daughter said, well, I really think that 8/9 of a meter is my length and my 5/7 is my width. That's okay. It doesn't really matter, right? And so when we think about in our 4D, right, our 4D space that we're talking about this week in lesson 23, and there's this infinite number of 3D spaces, right? So if I have 4 dimensions, I could be looking in my 3D-ness, right? I could be looking at length, width, and height. Or I might look at width, height, and breadth, or length, height, and breadth, or breadth, width, and length, right? If I can only see 3 of those dimensions at a time, it can be any 3 of them, right? Um, I, we tend, for the purpose of the patterns, right? We tend to say, okay, we had length, we added width, but we're just adding another dimension and we can swap those around. So for parents, when you see this and your student has reversed those, it's okay. It's just as correct as the answers that were given. So, and it's actually a great exercise, I think, with your students to talk about, right? If I'm only looking at one dimension of a thing, right? Does it matter if it's width, length, or height, right? You tell me something different about the thing, but I can look at any one of them in isolation. Right? If I'm going to look at 2 things, right, I can pick any 2 of those dimensions and so forth. Any questions on this exercise?
I did sneak one more in there.
Oh, good.
You haven't seen it yet, so hopefully it's okay.
All right, so here's another one. Can we clarify the instructions on the first question on page 10 of lesson 17, intersected shapes? The instruction says describe the intersections. I understand this is requesting the shape of the area common to both original shapes. Is my understanding correct? The answer key contradicts my understanding. So where the shapes, I think, are the original shapes. So Lee, tell me if I'm wrong. We're describing the original shapes that we were looking at here. So we're talking about triangles in the first 3 columns and octagons in the last one. So how are we describing them? We're saying these are the shapes that are intersecting. How many times do they intersect? And then what kind of a solution do we have? Is it consistent or inconsistent? And the hints are there, right, to help us see that we've got triangles and octagons, the 2, the infinite, and the 2, and then the consistent there for shapes. So yeah,
I see what her problem is. She's saying the area. So if you were to look at
yes,
right, she's just supposed to look at the
the
shape
original
itself.
shapes.
Yeah.
Yeah. So if you were saying what does the intersection look like? So in these cases, this intersection actually, I know you might think, oh, it's right, the part that overlaps is a triangle, but it's actually, right, it's this point and this point. So the shape of the intersections is just points. If we were to be thinking that way, but we're not. We're actually looking at what are the shapes that we're intersecting. And so sometimes here's a great example of us using an English word, describe, and we mean it in a specific way where we are saying we'll start with what you what you started with, how many times did they intersect, and so are they consistent or inconsistent? But we see how somebody might take that as be descriptive about what's happening. And in this case, we were not being as descriptive as I think perhaps this mom interpreted. A good question. Did anybody bring any questions today or anything they'd like to talk about? All right. So next week we're going to talk about rates. And I like the fact that we're going to build right into calculus. I think that it's really fun that we're introducing the grammar of calculus for our students early on, instead of setting that up as a gatekeeper, right? So our traditional education says that calculus is a gatekeeper. Classical education says, nope, it's not, right? That everybody has access to this. And so I'm excited that we're building towards that and making that accessible to everybody. Thanks everybody for being here and have a great week. Happy Valentine's Day. And we'll see you next week.
Yes, don't forget to have your kids send Valentine's in. I've only got a few so far. So send your kids Valentine's in.